All right. Cool. Hi, everyone. Thanks for coming out to listen to my talk today. For those of you that don't know me, I think most people do, but my name is Nelson. I work for a little company called Cotive. We do quite a bit of work. It's a lot of functional programming, reactive stuff. So a lot of Scala, a lot of Akka-based actor model things, a little bit of Node.js and Ember.js in a few of our apps. So we're going to be talking about that today. So just to kick things off, I'm assuming everybody here knows what React.js is, right? Okay, so just a little spoiler alert, that's not what we're going to be talking about today. There's a couple of guys when I talked to them about what I wanted to talk about today that sort of thought that this talk was going to be about React.js. So if that's what you came here for today, please don't leave. I promise I'll make it worth your while. So what is reactive programming, right? I think it's a bit of an obfuscated term that gets thrown around a lot, sort of like cloud computing and a whole bunch of other ones. And if you go around searching on the internet, you're going to find a lot of vague explanations on what reactive programming is. So obviously, I looked through the main places most people will go to, Wikipedia or Stack Overflow. Yeah, like I don't think those things, even to me today, that makes sense what they're actually talking about there. Eric Meyer had a pretty good presentation around what is reactive programming. I encourage you guys to go and see if you can find it on YouTube. But there's one part where he also goes through all the very over-the-top explanations on the internet. And the one that he mentioned that I thought was quite funny was the Wikipedia one, which he called the Dilbertesque definition. Okay, so I'm going to try to read this, so just bear with me. So in computing, reactive programming is a programming paradigm oriented around data flows and the propagation of change, which, if you think about it, sounds like pretty much everything that you do already anyway, to a large degree. This means that it should be possible to express static or dynamic data flows with ease in the programming languages used, and that the underlying execution model will automatically propagate changes through data flow. So quite a mouthful there, right? And if you actually think about it, that definition, pretty long-winded, right? If you have a look at that code snippet there, that's a piece of code that propagates changes through the data flow, is it not? Because you change the X value, and when you call the console log function, hey, look, your change has been propagated through the data flow, and it's been displayed on the screen. So, okay, that's reactive programming, guys. Thanks for coming. Just kidding. So the best definition that I could find on the net was this one, right? So reactive programming is programming with asynchronous data streams. Again, if you look at that, though, it's kind of vague. It's not anything new. If you've got some sort of event bus-based system or any sort of click-based event stream, that's pretty much what it is, right? But reactive programming is sort of an abstraction layer above that. It sort of takes away a lot of the complexities in building very distributed concurrent systems and sort of allows you to focus more on what's important. So speaking of abstractions, I want to sort of take a step back at this point. And I've got a little bit of a, I hope that's big enough for you guys to see. Yeah, a little bit better. Okay, anyway. So just having a look at this code sample here, right? So that's sort of an example of how you could use flat map. So at the top there, you've got a basic binary tree setup, right? With a value and a left and a right node. The left node can either be another tree node or it can be an empty. And then we run it through the function at the bottom there. So I don't know if you guys can figure out what that actually does. Maybe if I show a Ruby example of that. Sort of the same thing. Again, you've got the tree node, binary tree node structure on the left, and that same function on the right. Any ideas what that function does?
Sum up the...
Yeah, basically. So what that function does is it takes a tree node that looks sort of like that and basically gives you in a list or an array all the values out of the tree. So it recursively starts at the top and goes left, right, left, right, left, right till it gets to the bottom. Everything comes back up to the top and gets flattened out into a list. So if you had used map instead of flat map, you probably would have landed up with something that looks like that top. I don't know if all those numbers are exact. I sort of was tracing this manually when I was writing the code. But basically, so what flat map is is map and flatten, joined together, right? It gives you a lot of advantages when it comes to performance as well, because it's performing everything in one step instead of doing the map and then flattening second iteration over that. So you see that, like, flat map might look very confusing when you look at an implementation like that, right? But at the end of the day, all it is an abstraction over mapping and flattening out all the values into a common list. Right, so just wanted to use this as sort of an example of what abstraction is. So, you get things like monads and monoids and functional programming principles and reactive principles. They get thrown around, and we can get lost in the idea of what this is, or like some crazy notion of some higher order magic that's happening. But all it really is, abstractions are somebody had a problem that they solved over and over again, and they found a nice abstract way to take that complexity away and focus more on what's important. All right? So that's what reactive programming principles are, really. Just abstractions or ways to try and simplify our lives. And, okay, so I just want to take a step now back to the reactive programming and just talk about the main points of reactive programming. So reactive programming focuses around these four paradigms. So message-driven, asynchronous, non-blocking I/O, and back pressure. So message-driven, if you guys have ever used something like the actor model, so basically everything within your system, all the entities communicate with each other exclusively via messages. So no direct method calls or anything like that. You sort of have like a mailbox or some sort of bus that you send a message to, something receives it on the other side. Some good places to go look up info on this. This is a really cool article I found on TypeSafe. So it's the 7 ways to wash dishes. So it kind of goes through all the different paradigms, but it's a really good way. It takes a sort of a real-world example and sort of applies reactive principles to it. So like, he changes the way they're washing the dishes. Then instead of one guy doing all the steps, they sort of, split the dishes between them, and then you've got 2 streams of people washing dishes. So it's a nice abstract way to sort of, like, real-life world way of looking at how a reactive system would work. Then the concept of asynchronous. Okay, I think a lot of us, if you've done any JavaScript programming, you kind of understand the asynchronous stuff. Some good resources. You guys have to check out this ReactiveX library. So basically, trying to sum this down into a few seconds, but they've got the concept of observables for everything. They've got libraries written in JavaScript, for Ruby, for Scala and Java and all the different systems. They've got a pretty nice abstract layer for Android development as well. So if you guys are doing that, definitely check this out. But basically, they take the idea of, so in a synchronous world, you've got the concept of something returning a value, say a type T, or something returning an enumerable or an iterator of type T, right? So that's how you would synchronously process a for each loop or whatever coming back. So in this, they use the observer, and they abstract away the concept of synchronously waiting for something. So you'll have a future of type T. So you sort of have a callback that's almost like a promise, right? You wait for a result to come back true or false. For the iterables, they have the concept of an observer. And basically what you can do with that is just subscribe to it, almost like a message bus, and wait for each item to return asynchronously. But as far as your app is concerned, you're still processing it as if it was an iterator. So you can still use map and reduce functions over that asynchronous stream coming back. So, again, abstracting away the idea that now you're processing a stream asynchronously. So have a look at that library. It's pretty cool. Concurrent Ruby. This is also a pretty cool library. I found this during my search for this presentation. I'll talk more about this later. But basically, they've taken all the concepts of futures and asynchronous processing and all that, and they're trying, I emphasize the word trying to build a library in Ruby. A lot of the stuff isn't quite there yet, but it's definitely worth exploring. There are some pretty cool things there. Immutable data structure, stuff like that as well. Okay, so the concept of non-blocking I/O. So this is, if you look at asynchronous and non-blocking I/O, they're quite a similar concept. But this specifically looking at the concept of waiting for I/O, right? Using observables and things like that, it's pretty easy to abstract that away. But now when you've got the hardware side of it, potentially, you're talking to the network, you're talking to the disk. You don't want your thread to basically block waiting for that. If you look at, for example, JavaScript uses this, Node.js uses this library, by the way, to handle its async I/O. So basically the idea that you say, I want to read this file off disk, and here's the function that you must call when I've got the data. So your thread never blocks waiting for I/O ever in your Node environment, unless you specify so, which is a bad idea. I know there is some ways of doing that. So this is the library, the C library that they're actually using in Node.js to do all the async non-blocking I/O stuff. This is not necessarily, not specifically around non-blocking I/O, but this is a really, really awesome article, GitHub page that I found. Okay, the page is getting cut off. I actually had the shortened URLs for everything, but I'll put it up on afterwards for you guys to have a look at. The shortened URLs actually there. I don't know if you guys want to look up any of the pages, you can just grab that off quickly on your phone or something. This article here, I took a lot of material for this presentation. He basically goes through the idea of what reactive programming is, and he uses ReactiveX's JavaScript library with a whole lot of examples on how you would do asynchronous processing, non-blocking I/O, etc., using those concepts. And then back pressure. This is a really interesting one. It's quite new. There's a lot of the libraries. Netflix are using this a lot for their streaming stuff, and Scala's TypeSafe team are using it a lot in Akka as well. So the idea is you have data stream processing. So if you think about a synchronous system sending messages everywhere, and if you think about, I don't know if you guys ever used something like RabbitMQ or some sort of messaging system, the one danger with that is, what if your consumer is a lot slower than your producer? Eventually something's going to go bang somewhere, right? So normally you would sort of manually have some sort of manual process or automated process to scale out on the one side, or send messages, or sort of handle. You need to manually handle that process of making sure your buffers don't overflow. So the idea behind back pressure, and they've implemented this in Akka on Scala, is that the messaging protocol between streams actually takes care of that for you. So you have almost like a message being pushed up the queue that basically tells the producer to slow down, because I cannot handle the amount of messages you're sending me. So the idea is that obviously you might end up with a system that's slow with this, but never a system that crashes. So you sort of have that like auto management of the amount of data being streamed between all the endpoints. And they got a pretty cool DSL. So basically you say, this is my sink. They call it a sink. It's basically the guy that's syncing everything into the system, producing the messages. And this is my consumer on this side. And then you just say, okay, this is a consumer. He's going to receive this type of message. And this is what he has the code to process it. And this is what's going to come out. And you create all your points like that, and then you actually string them together with like a tilde sign. And then that's how your stream works, and you get stuff out on the other end. So it's a pretty cool DSL. It's very Scala-y, but you guys should have a look at it just to see what they're using there. And I think Netflix and a lot of the video streaming guys have got similar systems that they've built around the data streams for their stuff. Okay, so this pretty much sums it up for me, my take on what reactive programming is, right? So reactive programming raises the level of abstraction of your code, so you can focus on the interdependence of events that define the business logic. So instead of us having to worry about threads and how all this concurrent stuff is talking to each other and where you have locks and all that nonsense, you can take that away, abstract it away from your code, and worry about what your application is doing and not how it's doing it. So in my opinion, as well, based on these things we've been looking at, the actor model is actually a very reactive system, right? Or it follows a lot of the reactive principles. If you look at the principles that we talked about, so message-driven, your actors pretty much talk to each other via messages exclusively. There's no other way for actors to really interact with each other. Well, they shouldn't be if your framework is built properly. It is asynchronous, right? With the message passing between the actors, everything is handled asynchronously as well. So you can use actors to sort of help isolate blocking I/O. You kind of have to be careful with that kind of stuff from the point of view that you've got sort of a limited thread pool that any reactive system or actor-based system works with. And if you've got an actor now that's blocking on I/O, that thread is basically being held at all times. So you sort of have to be careful how you manage those kind of environments. But if you're in a situation that you have to call a library that you can't sort of non-block the I/O on it, then the actor model can sort of help you to abstract that away from the rest of your code and isolate where that blocking is happening. And also the back pressure concept. So as I said, Akka's sort of got that built in that you can make use of, but you can sort of manually manage the concept of back pressure. So sending messages up to pulling messages instead of pushing them, for example. That's one way to sort of help that out. Cool. And if you look at the way Reactive works, and even the actor model, I'm going to throw that in as sort of the same thing right now. It very much follows how the world works, if you think about it. Going back to that whole concept of the dishwashing, right? You could sort of take a coffee shop, that's the example I picked here, and sort of the way actors or reactive systems interact with each other through messages. Think of a coffee shop, right? You sit down at the table, you make an order with the waiter, right? You don't tell the waiter, you don't crack his head open and shove your order in there and close it back up. You send a message to the waiter and you say, I want a cappuccino or whatever. And you don't care what the waiter does with that message, as long as you get your coffee in a timely manner, right? And the same thing, the barista gets an order from the waiter doesn't care what the barista does with that, so long as at the end of the day, the coffee is already to take to his customers within a certain amount of time. So going on that point, I actually built a coffee shop simulator using the Ruby concurrent actor model. So I'd like to have a look at that now and just show you guys some concepts on some things I discovered while researching this presentation. Let me just sit down for this one. Okay, so this is, as I said, a simulator for a coffee shop. So there's a couple of things here that you couldn't actually simulate properly, like the actual. Oh, right. Sorry, I thought I'd made it bigger already. Can you see that? Is that okay? So things like actually physically making the coffee, I kind of abstracted that away as sort of like a wait timeout. So I've got the concept of time variances. Let me just go to the bottom here. So if you look at the coffees, right? So this is just the information that the simulator sort of uses to run. So these are the different drinks that a customer can order. And so for example, an espresso there, if you look at the top, takes at least 25 seconds and at most 40 seconds to make. So the whole simulator sort of works on that concept. It takes a random variable based on the data in this file, and that's the amount of time that the actor will sort of sleep instead of actually working, because I couldn't make the simulator actually make a coffee, but that would be great if you could do that. So we're just sort of simulating that part. So if you look at the code, for example, the customer, just going to the bottom here. So these are the things, so the scheduled tasks that we're running here are basically to simulate those wait periods. So these are the amount of time, this handles the amount of time that a customer would wait to be seated at a table, wait to be served a drink, and wait for the order to arrive. So what I did over here, I wanted to try and keep it as asynchronous as possible. The other thing, I forgot to mention, that actors give you is a nice way to isolate your state. Every application has a certain amount of state. As much as we'd like to get rid of it completely, it's not possible all the time. So you isolate your state within the actor, and the actor always runs as a single thread, right? So the problems with multi-threaded locking and all that kind of stuff kind of goes away. And if you write your apps correctly, you can isolate your state nicely to a single threaded environment. So the way that the actors would work in most of the frameworks, you could have, say, like 100,000 actors running and a thread pool of 100 threads. Only when an actor gets a message will he try and get allocated a thread in order to work. So you could have millions of actors, technically speaking, in a system and not have your system crash because of the way it's been designed with the thread pool. Obviously, you could run out of threads if you've got a million actors if they all try to run at the same time. But, can't have everything all the time, I suppose. So what I try to do here with the wait is I run a concurrent scheduled task. So what this does is it starts almost like a timer. So you see that I take from the consumed drink variable a sample time. So how long this guy's willing to wait for his order to arrive before he gets pissed off and leaves. So that sort of runs in the background. When the scheduled task is scheduled to run, it starts up a thread, and this runs in a thread outside of the customer actor. So what I did there is I actually sent a message back to the actor so that when the processing is actually done by one thread inside the actor at all times, if that makes sense. Going back up to the top here, so this is the on-message stuff that gets received. What I tried to do here, I don't know if you guys have played with Elixir at all. The way they've got sort of the concept of a tuple being sent as the message. So the first part of the message is an atom, or in like this case a symbol, that indicates what this message is. So if you look there, the customer was seated. He's been told to go find a seat at the coffee bar. I'm done, or I'm annoyed, so I'm leaving. So we sort of log the reason why he's leaving, all that kind of stuff. So the first part of it is sort of indicating what kind of message this is, and the second part is an array or a single variable with the information on that message, like the data for that message. Going back here, so this is probably the most complicated out of all the actors, is the maitre d'. Okay, so I'm going to run the simulator now, but just give you an idea of what happens in this thing. So we've got a list of customers that arrive. You look here. So we've got the customers that are arriving at a table. So this is just a little YAML file, config file, right? So these 3 customers arrived at the same time. They're together. Then this guy arrived separately, then 4, etc., all the way down. And then these are the single customers that arrived to be seated at the coffee bar. So the coffee bar actor starts up, it's the actor for the coffee shop, and it randomly picks these customers from these lists until all the customers have arrived, and he passes it to the maitre d'. The maitre d' tries to seat them at a table, or if they want to be seated at the coffee bar, he sends them off to the coffee bar. So the customers for the table get seated. If there's no seats, they will get put onto a waiting list. And then the maitre d' will keep checking to see when the tables are empty. They're only willing to wait a certain amount of time, and then they'll leave if they're pissed off, right? The guys for the coffee bar will try and go to the coffee bar and find a seat. If there's no seat, they go back to the maitre d'. The maitre d' then tries to seat them at a table if possible. If not, they also go onto the waiting list. And they constantly check the coffee bar and the tables to see when there's an available seat. Okay, let me run this thing for you guys to see what happens. The other thing that I did as well, these times in seconds, of course, would be here forever if we had to wait 60 seconds for like a seating time variance and 5 minutes for an arrival variance. So I've got a speed up factor. So I'm speeding this up by a factor of 1,000. So 60 seconds is 0.06 seconds. Just so for the first run. I'll slow it down for the next run. Yes. All right, so yes. Okay. Yeah, there it says it's running pretty fast now. Just wanted to run through. So all these communications here, it's all actors with messages being passed to each other asynchronously. Of course, with the random time variance, you'll find that the next run looks completely different every time. But so there's the stats from our run. So 6.6% of 6% of our customers waited too long to be seated and they left. You can see that doesn't look too great if this was a real coffee shop. Half our customers left waiting too long for an order to arrive. Yeah, so there's all the stats for that. There's the drinks that were ordered by the different customers. So there's the reasons for customers leaving. So that's pretty bad. 62% of our customers left because they waited too long for an order to arrive. So what's going on here with our system? Let's have a look at our settings, right? So we've got the customers. So here's the settings for number of waiters. We've got 4 waiters, 2 baristas. So if you think about it, we've got 2 baristas making coffees for everybody at all the tables, plus like having to serve the people that are at the coffee bar as well. So that might be a factor here, I'm not sure. What I did with the total coffee machines, it's more of a concept of how many coffees could be made at the same time, the amount of equipment. So let's change these up a little bit, shall we? So let's make 5 baristas and increase our equipment. So 2 coffees can be made at one time. Let's see if that helps. I'll slow it down a little bit so you guys can actually see what's going on with the logs. I have 5 baristas. Yeah, this is more interesting. You can play around with it later. Yeah, I could do that. So the idea behind this is if, like, you want to have as efficient a ratio of waiters and baristas to customers. So let's try that. So I'll slow it down a little bit for us. Let's run this again. Okay, you can see that thing's a little bit better now. It's slower. So you can see there at the top, so the tables were allocated to the waiters. And now everyone's being seated. So the yellow is the baristas, the pink is the maitre d', the blue is the waiters. And you see as it starts getting towards the end, the thing starts slowing down as most of the customers have left already. You see most of the interactions really is just between the customers and the waiters and the baristas now. Maitre d' is not doing much. I think it's almost done. We've got like 1 or 2 customers left. I think maybe I'll make it 500 next time. It's a bit so.
Is that order multiple drinks?
Yeah, so it's randomly anything from 1 to 5 drinks. So they'll order a drink, then they'll finish their drink, then they'll wait for the waiter to come back, and if it takes too long, then they'll leave as well because they're pissed off. Yeah. See, it's slowing down now because basically, and there's only 1 or 2 customers left really ordering drinks still.
Thanks for staying late.
Yeah, this is the late guys now.
Dim the lights.
And the waiter's constantly waiting for the guys to leave. There's finished. And there's 1 more guy left, I think, still. Yeah, he just placed an order. Somebody got pissed off for waiting too long. There he's having his last drink. Another one. Yeah. There we go. Okay, so that's the full simulator run. So a little bit better here. 70% of our customers left happy. So probably, yeah, we'll find we need to increase our coffee equipment. But yeah, anyway, so you get the idea of the simulator. Yeah, I think that's pretty much it. So what I did here with the code structure, right? So every entity was an actor. So you have the concept of a waiter and a maitre d' and a customer. I don't know if you noticed, I mean, like to add more baristas and more coffee machines was basically just incrementing a number. I didn't have to change anything in the code. Because of the way everything is sort of isolated and sort of asynchronously talking to each other, it's easy to sort of scale things out. If you can imagine doing this with threads, it might add some more complexity into the system. Cool. So, yeah, that's me. Thanks. Any questions? Don't forget any questions.
So this code is on GitHub?
Yes, it is. It is. But this is the Impress.js presentation and the coffee shop simulator is there.
No, it's a big to play around with it.
Yeah.
That is really cool.
So how would we use this, like in background workers kind of stuff, or is this something you can do during a Rails request response kind of thing?
You could. So the idea behind the actor is it's supposed to be easy to spin up and then easy to dispose of. So it really depends on like your environment. The one example I remember they showed in one of the courses we did for the reactive programming is like a web scraper. So they had like sort of the main control actor that sort of lived, and then he sort of farmed out requests to a bunch of actors and waited for them to finish processing, and then he'd shut them down, and he'd sort of keep farming out actors that way. So, it really depends on the scenario. But yeah, the idea is that they should be cheap to spin up and to shut down. Unlike real people, they're easily disposable. Well. Even real.
What's with your I/O blocking stuff? What does it actually do to try and negate blocking
Mm-hmm.
So with the libuv library, that actually uses like the operating system level stuff to handle it. So you've got sort of like at the kernel level messages that libuv will pick up and then sort of push up to your callback in your code.
So does it just cause it to, I don't know, I mean, your blockings normally just ends up waiting because your table's locked or something.
Yeah. If you think about the way most database queries in that work, that's blocking I/O, right? You wait,
Yeah.
and that thread can't do anything else. If you think in a Node.js environment or like in a JavaScript environment, that's pretty bad, right? So that's why I think that they have that libuv library there. It's like a very important part of it. Never block the main thread because there's only one of them.
But there's, I mean, nothing specific like code-wise that it's just using the operating system to handle it to some extent?
Well, I
hardware?
suppose it's a very low-level thing. So a lot of times you would sort of have a library and rely on it. Like the Slick library in Scala, which is basically like a database ORM, sits on top of the JDBC stuff, and that wasn't asynchronous, non-blocking. So that you could get into a lot of trouble. So you'd have to all like manually abstract it away using actors or something. But again, you're left with the problem that if you're doing 1,000 database queries in parallel, that's 1,000 threads that are pretty much stuck. So that's the danger of that. You have in a lot of the asynchronous reactive stuff, you have the concept of, like I said, a thread pool. So you can run out of threads. That's a problem when you block on I/O.
And if you're running out of thread, or I don't know, you're just timing out because you're waiting too long for those threads to complete, is that something that this solves?
So that's one of the pains of the asynchronous stuff is, you send something out, you expect a callback within a certain time. With a lot of the active stuff, you have sort of like timeouts that you specify. So if you run out of threads, you're expecting it back in a certain amount of time. Your stuff's going to time out and stop working. And I think that's the idea behind the data streaming stuff as well, is to try and don't crash, slow down, but don't crash, All great ideas, but there's a lot of work still to be done around that kind of stuff. And you have to be careful with what libraries you use, etc.
Cool.
How was your experience? I just did the course 2 years ago, and what I found a bit difficult, and it's just when I had to do the assignments, is sometimes to kind of debug, because you send a message, and is there did you find you've got more experience, or did you find tools or like kind of things that you normally don't do in a more traditional kind of language to debug? Or?
So like sort of if you've done JavaScript programming, you probably have that same headache, like where your errors or your code seems to just stop somewhere and you don't know where it is. So like doing proper error handling with like a promise or some sort of future-based thing is important. Helps a lot with that. So you've got asynchronously stuffs all talking to each other, catch the errors and make sure they propagate up to a point where you catch them. That helps a lot, because then that's when you land up with things sort of stopping and you don't know why, because the errors now disappeared asynchronously somewhere. The other thing that helps a lot is testing, right? That's a good way to catch, because you sort of isolate your actor or your asynchronous system and test that. Because it's a message passing sort of isolated block, so it's quite easy to test. If you pass a message in, you should get that out. That helps a lot, sort of isolating and testing the individual actors. And sort of dependency injecting where you need into your actor if it's got some sort of database library. If you dependency inject that in, now it's easy to sort of abstract that part out.
Cool. And I know when did you do the course?
I think it was December I did it.
Because I've not looked at AK after, but is it more mature? Because it was kind of very unstable at that time and so on. So it's
they've improved it quite a lot. They've also got some cool things that they've added now for persistence into it. So if you've got your actor sort of running, and imagine like your machine or server crashing, right, or your instance, your VM, if you can sort of give it like a persistence layer, so it persistent state. So when you bring up the system, all the actors come back in that same state and they continue working. So like for switching VMs and things like that can be handy. You can sort of pause, persist, swap it over and carry on running, which is quite cool. Easier said than done though.
Yeah.
Something else was my experience with Reactive programming. So object-side Reactive extensions for .NET. I think it's a simple Reactive X. And it lets you do quite a lot of interesting things between things that actually consume the messages and things that are published, for example, rate limiting, so that's your concept of bank ratio. Anything that publishes an event in a UI kind of way, something like JavaScript, moving your mouse publishes events that you could observe on that. And okay, so the problem with enumeration is not that doing a for loop over something is that every time you consume something, you need to know whether you're at the end of your list, so that you can stop blocking and continue. And this solves a lot of those problems because it's just if there is something else that gets sent to you, you don't need to worry about whether you get to the end. And that also helps memory consumption. You don't need to build a whole list of things before you consume them.
Yeah, and again, like
things like that. So like you only want to capture one per millisecond, not 100 per millisecond.
yes.
Just separation of concerns.
Yeah, and also then again the way it handles the threads for that as well. So if it's waiting for something to come back, it only allocates a thread when a message is ready to be processed by your stream. So you'll never notice that the way you've written your code and the way you're thinking in your head is just another loop, right? You're looping or iterating recursively. But it's actually every time something comes back, then a thread gets allocated to process your code. And when you're waiting for the next one, then the thread goes somewhere else. So it's really around, like, a lot of these things also around sort of being efficient with the way you handle your threads, which is very much a finite asset. And not just that, but abstracting the idea of having to worry about threads as well. So abstraction, right? Layer above all that stuff, thread blocks and mutability and all that nonsense. We don't have to worry about it anymore. But of course, we'll probably find other problems. And then, like everything, there'll be something else that will come out on top of this and abstract more of that complexity away. That's what we do, right? That's learning all the time.
Things that you at CATSAT says like we're building on the 200th floor of a skyscraper. Like sometimes you need to go down like a few floors to understand, but you don't need to go to the basement. Like you can just keep building up.
Yeah.
I was thinking this is probably the principles that are used with games that have RPG elements in them. So think of like World of Warcraft. You get like a piece of a weapon, a piece of armor that gives you kinds of buffs or whatever, and they trigger when certain things happen, and when certain things happen within they trigger. And I can imagine that implementing a system like that would be near impossible without having some kind of reactive programming foundation running everything like that.
Well, imagine what it, like how scary it must be to work on that code, and if it isn't.
Yeah.
So, was it Len that was speaking to me a while back, like all these things about having immutable code and functional programming principles, and that a lot of it's got to do with the fact that we're now, we've got the multiple cores. So, if you've got the immutability, makes it easier to sort of predict when you have certain inputs, your outputs are sort of guaranteed to be that. So it makes it a lot easier for the processors to sort of spread the work out themselves over the course. That makes sense.
Does make sense.
Cool, man.
Thanks very much.
Thanks.
Yeah, cool.
Thanks.